Today I will be discussing on a work of upgraded stability and measurability in a compound penta-BCN by the process of fluorination. A full version of this work is published in Applied Surface Science, so if you're interested, I can provide you the link at the end of this presentation. I would like to start this presentation with this interesting paper by Professor Cranford, who discussed the penta to hexagraphene transition and describes the importance of pentagonal based compound. If you go back to the evolution and synthesis history of the pentagonal based low dimensional compound, then it all started back in 1950s with a special organic compound. Then in later years, in 2000s, the carbon 20, the buckyball, and the first pentagonal based 2D compound, pentagraphene, in 2015. The pentagraphene was first introduced theoretically and predicted to be stable and demonstrate a high value of negative Poisson ratio and semiconducting functionality. Then in 2016, the pentagonal based silicene was synthesized experimentally. Then other compound like penta-PDSE2, penta-NiN2 were also synthesized experimentally. There are a wide range of applications of this material, ranging from energy, mechanics, spintronics, catalysis, electronics, and so on. But these materials are still getting less attention in the research community. Moving beyond the monoelemental pentagraphene to binary PDSE2 and so on, recently the compound penta-BCN is introduced, and it is claimed that the compound exhibit novel properties such as semiconducting functionalities with high value of intrinsic piezoelectronic tensor and high mechanical strength. But it is found that this compound still exhibit a small value of positive formation energy and dynamical instability issues when the material is compressed mechanically. So in this work, we will demonstrate how we can establish the mechanical stability as well as chemical stability by the process of fluorination in the pentagonal based BCN compound. So I will discuss mostly here the geometry and structure of the fluorinated compound, the theory involved in this computation process, stability test, as well as the mechanical enhancement and upgrades in this compound. So we perform the density functional theory calculations using the code C star mostly, and we use the BASP for ab-initio molecular dynamic calculation. So we can see the fluorinated boron carbon nitride, and we design this compound by passivating the fluorine partially on the top and bottom layer of the pristine BCN, which is composed of three ingredient elements, boron, carbon, and nitrogen. And we can see the different planes and the corresponding the bond analysis by the molecular charge analysis calculation. And we found that the boron nitrogen, boron carbon, and boron fluorine are covalent in nature, and the carbon nitrogen fluorine is ionic in nature. Further, we checked the stability test, and we found that the materials now exhibit the negative formation energy and the cohesive energy, and indicates that the fluorinated BCN is chemically stable. Further, we performed molecular dynamic simulation using NBT symbol up to the time 3500 femtosecond, and we found that The geometry is stable without any destruction or bone breaking. And further, we confirm the dynamic stability by performing the phonon calculation, the non-imaginary bands, and the phonon diagrams, so that the compound is dynamically stable, which is lacking in pristine form. Further, we test the mechanical strength and stability calculation. The bone criterion was used to see the stability criteria. First, we calculate the elastic tensors, and we compute the Young's modulus, 2D Young's modulus and Poisson ratio using these relations. And we found that the material exhibit almost similar strength to the pristine counterpart. And not only that, when we apply strain along the biaxial direction, we found that the compound can tune the mechanical behavior. The compound boron carbon nitride in fluorinated form shows that mechanical strength up to 220 Newton per meter, while it is compressed by 6%. So further, we check the orientation dependent mechanical properties, and we found that the material exhibit isotropic mechanical response. We implement these relations to compute this polar plot, and it is clearly demonstrating the isotropic mechanical behavior, which was lacking in the pristine form. Further, we apply high order mechanical strain to find the critical point, and along the x-axis, y-axis, and along the both axes. The strain along the x-axis is represented by epsilon x, and along the y-axis by epsilon y, and epsilon xy is for the biaxial strain. So we found that the material shows good strength while we stress the compound along the y-axis. We can see the geometrical destruction after the critical point when we apply the strain in the figure. Okay, the conclusion. We conclude that the fluorination in penta-BCN increases the chemical stability and helps to achieve the negative formation energy, and it also fixes the instability issues of phonon and mechanical instability in compression strain. It also enhances the mechanical isotropy, and it can be used to tune the elastic behavior in different range. And we can conclude that fluorination is the best possible way to tune the properties of pentagonal BCN. So I would like to acknowledge the co-author and my professors who contribute to this work. So thank you very much.